Hey everyone, a very happy Tuesday and welcome back to our ARM Tech Talk series. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. And I'm thrilled you can join us today, wherever it is you're joining us from, if it's your first thing in the morning or last thing in the evening. Really excited to have you here today. And we're joined by ST, who are going to be talking about how you can accelerate your AI project development on STM32 MCUs. But before we get to the real meat of today's topic, I've got a few little housekeeping slides I just want to go over very, very quickly. If you've attended one of the 70 or so tech talks we've done before, you'll know the drill on this one. But if you want to get involved in the conversation, you can, of course, tweet us or post on LinkedIn using the hashtag ARMTechTalks. As I say, all of the tech talks we've done, I think we're near 70 now, which is just phenomenal, are all on demand. They're available at youtube.com/ARM. So make sure you head to our YouTube channel and hit the subscribe button so you don't miss anything. And all of our upcoming talks are always posted on arm.com/techtalks. And here's some that are coming up. We've got ST today. We're just finalizing the title of a very exciting tech talk by Arduino in a couple of weeks as well. So look out for that one. We're going to be joined by a very special guest from Arduino. If you know the company well, you can probably guess who that's going to be. I'm super excited for that one, as well as our AI partner, Digirum. That's on July the 18th, before we have our summer break. And then we're right back at it in September. But let's get to today's topic, right? This is what you're here for. I'm thrilled today to be joined by Nicola from ST, who's a product marketing manager in their AI solutions team, as well as his colleague, Mohammed Shanawaz, who's an AI enthusiast and data science and algorithm engineer in the AI solutions team at ST. So I'm thrilled they can join us today. So let's get Nicola set up. His camera and microphone on. He's just coming on now. And I'll let him take it away with today's ARM Tech Talk. Before I do hand over to Nicola, though, if you've got any questions at any point in today's webinar, please use the Q&A box in the menu bar at the bottom, and we'll get to those at the end. So Nicola, I'm thrilled you could join us today. Really, really excited for today's tech talk. So why don't you take it away and tell us how this audience, the audience that are joining us today, can engage and enjoy the STM32 platform and the Cortex-M that powers it and your AI developer cloud. So great you can join us, Nicola. Take it away with today's ARM Tech Talk, please.
Hi, everyone, and thanks a lot, Tobias, for the very nice introduction. I am also extremely pleased to be here today and to open this webinar by presenting our solutions for embedded AI on Arm Cortex-M based STM32 microcontrollers. First of all, I wanted to start this tech talk by a short reminder of STMicroelectronics' mission in the field of embedded AI. Indeed, our mission is to democratize embedded AI with STM32 platforms by bringing industry-leading tools for AI at the edge. Since the inception of our first solution, we are working every day to build the most comprehensive software stack in the industry to support our clients in their edge AI journey on Cortex-M cores. We are convinced that edge AI is the future of embedded devices, and this is why we are striving to develop highly differentiated software and hardware solutions. So in today's webinar, you will learn how to use STMicroelectronics tools in order to deploy an image classification use case on a Cortex-M7 based STM32H7 microcontroller. In details, the hands-on session will show how to achieve around 9 frames per second flower recognition application with an OMV BCam camera module using our STM32 Cube.AI toolset. We will have 2 speakers in the presentation, as introduced by Tobias. I will now start with some marketing information, and then my colleague Shanawaz will follow by walking you through the hands-on part. Now, developing an AI project at the edge on a microcontroller is definitely not an easy task because it requires to have access to clean data, people with a wide range of competencies, and also being able to deal with the hardware constraints of edge devices. Moreover, it's not only about hardware, but one extremely important challenge is that until recently, the level of the available toolchains made it very difficult to deploy industrial-grade AI projects. Focusing now on the challenge of deploying a trained neural network on an MCU, here's the situation. So I have a trained neural network, I have a dataset with which I have trained my neural network, and I want to fit the trained network within a resource-constrained microcontroller. How do I do it? How do I check that the model can be really embedded within my STM32 platform? And how do I evaluate the performances I will be really able to achieve? And this is what we will show today. So to address these challenges, STMicroelectronics has developed over the years a large product offering targeting various applications, hardware devices, and user profiles. As you can see, our tools cover the field of automated machine learning and deep learning on MCUs, but also AI on microprocessors as well. And all typical AI fields, such as time series, audio, computer vision, are part of our customers' applications. As part of today's presentation, our focus will be on STM32 Cube.AI technology, and I'll show how it is easily used to deploy embedded AI on an Arm Cortex-M based MCU. At ST, we wanted to make sure that anyone could easily develop embedded AI projects. And this is why, on top of our STM32 Cube.AI core technology, we have built over time a complete ecosystem of solutions to accelerate the development of your AI projects. Our tools are here to make you succeed in this task, even without the need for you to be an AI or embedded software expert. And I will shortly explain this solution in the next slide. But before that, you may wonder, why do this? It is true that there are other solutions available in the market for optimizing artificial neural networks on Arm Cortex-M cores. Well, actually, no other solution is better placed than STMicroelectronics to do it on Arm Cortex-M based STM32 microcontrollers. Our solutions are fully integrated in the STM32 development environment, making it a seamless task for people to use AI on STM32 platforms. STM32 Cube.AI has been specifically designed to guarantee the best performances on STM32 MCUs by leveraging a total knowledge of the hardware. And doing so, we definitely achieve top gains in terms of power, inference time, and memory usage as compared to traditional tools and solutions. For instance, by deploying an optimized code on an STM32 with STM32 Cube.AI, we guarantee that you can achieve up to 60% gain in terms of inference time and up to 20% less flash and RAM occupation as compared to the same workload using TensorFlow Lite for microcontrollers. And on top of it, our solutions are completely free of charge. You can thus access to leading AI performances on Arm Cortex-M based MCU with not spending any fees. So now, before moving on to the hands-on presentation, let us have a closer look at our solutions. First of all, STM32 Cube.AI is a tool to optimize AI models to run efficiently on a resource-constrained MCU architecture. It allows to easily evaluate, optimize, and deploy machine learning and deep neural network on all STM32 portfolio. Cube.AI has been thought to be seamlessly integrated within our machine learning development flow by taking as an input standard pre-trained neural network format from any major AI frameworks. So either directly in Keras or TensorFlow formats, or by using the no standard ONNX format, which can be generated in most of the cases by all the frameworks. Once the model is imported in STM32 Cube.AI, the tool will optimize the network for STM32 targets, evaluate the hardware requirements to execute such network, processing power, inference time, and memory footprint. Performances validation can be done directly on the target connected to the computer, and you can also visualize more details such as execution time per layer and memory usage per layer. Finally, once the right MCU is selected and the model is validated, it's no time to choose the type of output you need. And either you can only generate your optimized C code, you can also generate some firmware for performance validation application, and you can generate two STM32 Cube project files, such as the MX IOC file or the IDE project file. Because we are continuously improving our offering and facilitating our users' work, they have now access to two versions of the tool, depending on their profiles and what they are looking to do. On one hand, we have the original desktop version, mainly targeting embedded software developers who are used to the STM32 Cube ecosystem. For them, it's a native integration in this ecosystem because it is a package which is easily downloaded inside the software. It is also available in command line interface to easily script your AI deployment. And it is connected to the rest of the STM32 Cube ecosystem, so IDE, programmer, so on and so forth. And on the other hand, we have the online developer cloud version, mainly targeting data scientists and AI developers with knowledge of artificial neural networks, models and tools, but with few experience of the embedded software world and tools. So the developer cloud is an online platform offering the Cube.AI services directly on the web without the need to install any tools on your computer. To get started, all you need to do is to connect and log in. That's a pure digital experience, no software installation, no hardware needed. It allows you to benchmark your model on real hardware using our STM32 board farm. Indeed, with the developer cloud, you can access the real inference time of your model running on real silicon and benchmarking a broad range of hardware by comparing the relevant metrics, accuracy, latency, RAM, and flash sizes. You can then easily identify which hardware is the most suitable for your application and move on with it. We are also providing REST APIs and Python wrapper to streamline the integration in your machine learning operation flow. More recently, in order to inspire AI developers and to kickstart the developments of new embedded AI projects, we have released our own collection of pre-built models and scripts that we call our Model Zoo. STM32 Model Zoo is a public GitHub repository of AI models, scripts, and application examples, tutorials to support and guide our users through the process of developing optimized application on STM32 targets. The goal, by selecting one of the provided examples, the user will get access to a full set of resources to easily process their data set. They can train the neural network with our script. They can evaluate them, the neural network on STM32 platform, and they can even deploy the generated optimized code to the board connected to their computer. Our Model Zoo is obviously continuously evolving, improving, and we are adding very regularly new use cases, code examples to make your life easier. So with STM32 Model Zoo, it has never been so simple to generate AI on a Arm Cortex-M based STM32 microcontroller. Finally, as mentioned before, our developer cloud is connected to our STM32 board farms, thus enabling users to test their model in real time on the STM32 of their choice, and all of that free of charge. Today, we have around 10 boards available in the farm, and we are adding new ones upon request from customers and partners. So using the board farm allows you to get access to the new STM32 platforms as soon as they are released as well. One last word before passing the microphone to my colleague Shanawaz. STM32 Cube.AI covers the entire STM32 series of Arm Cortex-M based cores, meaning from Arm Cortex-M0 and M0 Plus up to Arm Cortex-M7. This is not only available for future developments, but also for devices already in production in order to make them definitely smarter and to give them a new life. So that's it for my part. Would you like to learn more about STMicroelectronics AI solutions? Please visit our dedicated web space where you will find all the details about the tools, useful resources, and use cases examples as well. Now, moving on to the cool stuff with Shanawaz taking the lead for the rest of the webinar and driving the hands-on session. He will show you how to easily develop an embedded AI project using our tools in 3 steps. So Shanawaz, the floor is yours.
Thank you, Nicolas, for the introduction and providing the information on our offerings. So as Nicolas was showing the website, I'm on that website where you find all the information related to what we are offering in terms of AI. In my session today, I would be describing 3 different things and doing the walkthrough with the hands-on. The first item that we'll have a look on is the STM32 AI Developers Cloud. To go to the Developers Cloud, simply choose the products drop-down and go to the Developer Cloud. On the Developers Cloud, web page, you have all the information and documentation on the web cloud, what are the features and what you can achieve with this. As Nicola said, this is something which is quite equivalent to STM32 AI local installation, but is more powerful because it comes with a cloud form of the actual STM32 boards. So you can do the benchmarkings on these actual boards and get the footprints and the inference times on the real boards. So to go to the developer cloud, simply press the button, open online platform. Once you are on the developer cloud tool, you just have to log in. To log in, you can create a MyST account for free if you do not have one already, or you can log in if you have one already. Once you have logged in, you come to this landing page. On this landing page, you see three main spaces. The first space is to upload or provide your own model. You can do the uploading by either pressing the upload button and selecting the model to upload. For me, for example, I will be using the Flowers MobileNet dataset model, which is trained on Flower dataset with a MobileNet V2 architecture of alpha equal to 0.35. Or you can choose a model from the model zoo, where we provide variety of models which are trained for 5 different use cases. These models are pre-trained with the public data sets, so you can import any of these models in the third space, which is the workspace. So any model which you upload or any model which you import from the model zoo to do the project in the developer cloud will come and appear in your workspace. To start the project for your from your workspace, you simply click on the start button, and this will start the project by importing your model from the workspace to a developer cloud project. So after your model is imported from here to your developer cloud project, it is going to do an analysis and provide you some footprints of your model for STM32 AI targets. It provides you the footprints which are in terms of flash, both the flash required to save your weights as well as the flash required for your library, and also the RAM, which is going to be required to save your activation, as well as the RAM required for your library. It also provides you the computational footprint in terms of max. For the optimization of this model, we provide 3 different options. By default, the balanced approach is selected, which is a trade-off between providing you the best RAM footprint as well as the smallest inference time. But you can choose any of the 3 to run the optimization and to get these numbers. Once you have optimized the model, you can go to the quantization. The step for the quantization uses post-training quantization based on TensorFlow Lite converter, and we provide 3 types of input and output possibility. You can use either signed integer 8, unsigned integer 8, or float 32. To do the quantization, you can provide that part of the training data or the training data itself by simply providing this in the form of .npz file format. To know more details on how to prepare this NPZ file, you simply click on the information bubble icon, and here you find all the information and code examples to prepare the file. Or in cases where you are using a public model and you do not have the access to the training data, we provide the possibility to do what is called fake quantization, with which we use the random data as an input to do the quantization for you. To do the quantization with the fake data would result in loss of some accuracy, but nonetheless, it would provide you the real footprints for your quantized model once you have done the quantization and the benchmarking. Now I'm running the quantization using the fake data or the random data. And after the quantization is done, a model would appear here, which would be showing me a TF Lite model. This is equivalent for you to do the TF Lite based quantization locally on your PC. In the meanwhile, I would like to talk about the terminal output over here. So you can see all the information related to what's happening in the cloud is shown in the terminal. If there is a problem, you will see there is a problem here, but it has successfully quantized the model. And now it's doing the analysis of the model by applying the same optimization, which we selected in the first step, which is the balanced optimization. Here you can see the max now have decreased from the original number, and also the flash size and RAM size has decreased compared to the original number because we are using the integer 8 representation for our weights as well as for the activation. From here, we can go to the benchmarking step where we can do the benchmarking or profiling of our model on different STM32 boards. To cover the variety and wide range of STM32 boards, we provide different boards which are based on Cortex-M4, Cortex-M7, as well as Cortex-M33. I will be doing some benchmarks on Cortex-M7 boards. Another thing to tell you over here is that you can launch the benchmarking on multiple boards at the same time, and this would be happening in parallel. You do not need to wait for one of them to finish before you can launch another one. And here, your model which you provided is being optimized. Then this model is being quantized. After this quantized model would be converted into optimized C code for STM32 target boards. This would be then copied in system performance application, and then a project will be building using Cube.IDE, and then this project would be flashed on real STM32 silicon, so that you can have the real results of your inference time as well as the results for your footprints. This process takes roughly 1 to 2 minutes, depending on your model size or depending on which board you are using. While this is running, I can show you that after there would be a list of all the runs you have here, displaying the device on which you did the benchmark, as well as the footprints would be appearing here as soon as the model is going to finish after doing the benchmarking. You can also notice that the board corresponding to G474 is blurred. The reason for this is that this board does not have enough resources to embed this model on this board. So this makes your life easier to tell you already that you cannot use this board, for example, for this model because it does not have enough resources. Also, you can see we mentioned the information about the internal as well as the external RAM. The tool is configured in a way that if your model can fit with the internal resources, it will only use the internal resources. But if it needs the external resources as well, it would use the external resources and automatically configure your model generation in a way that it would be using the external resources. And it would give you an indication at the result section. So the benchmarking has finished. As you can see, the inference time is reported next to the board on which we ran the benchmark. We can see that for H735G, we have 78 milliseconds, as well as for H743Z, we have 89.57 milliseconds per frames per second. So here, for example, you can see the reason for this is because we are running on the faster clock for H735, so it has smaller inference time. The next step, as my colleague Nicola told you, that we provide also the possibility to have the details per layer. Here you can see, for example, the flash required to save the weights for each of the layers individually in the form of a bar chart. But you can also toggle between bar and pie chart where you see the proportional area or the proportional section of the pie chart telling you each of the layers is taking how much of your weights. This is a very useful feature because then you can optimize a given layer which is taking more resources instead of optimizing all the layers. We do the same thing for the execution time, where we plot the bar charts to tell you how much time is spent on each of the layers. And similarly, like the weights bar chart and pie chart, you can toggle between pie chart and bar chart for the execution time as well. Once you have done the benchmarking, you can go to the next step in the results. Here we have also the possibility to export the results of your runs as a CSV file, which contains all this information in the form of comma-separated CSV file. Or you can show the performance summary in terms of a scatter chart. This plots a scatter chart for your model benchmarks on different boards available on STM32 AI Developers Cloud. Here, for example, it shows you how much time is spent for one inference on each of the two boards for which we did the benchmarking. Finally, we can go to the generate section and we can generate the optimized C code for our model. To do this, you simply have to select your CPU series. For me, I would be selecting the Cortex-M7, and then this would apply a filter, and you will see only the target boards which belongs to Cortex-M7 family. As you see here, even in Cortex-M7, there is one of the MCU which does not have enough resources to embed this model. So this is already provided in the form of a warning here. Then from here, you can choose the board for which you want to generate your model code. And I would be simply selecting any one of the boards. For example, I can select this one. After this, I can generate the optimized C code for my model in 4 different formats. The first format is simply to download the C code. This will download a zip file, which will have the optimized C code and all the associated header and runtime libraries, which can be used to embed in any STM32 embedded project. Or I can generate a Cube.MX IOC file, which would have a zip file with the model itself and an IOC file, which can be used to create an STM32 Cube.MX project. The people who are more used to doing the embedded development, they are aware of this. Or you have the option to generate the Cube IDE project directly, which would have the IOC file as well as the model and the optimized C code for your model. Finally, we also provide a possibility where you can download a .elf file directly and flash your board with this one. This would have a system performance application, and by running this one on and connecting your board with the Terraterm, you will be able to see the inference time and the performance on your board. The next, I would show you, I would take you to the Model Zoo, which is the next offering we have. In the Model Zoo, we provide a full life cycle of AI projects. With the Model Zoo, we provide the possibility for the embedded developers as well as for the data scientists to build a model, to train the model on their own data set or one of the public data sets using a public topology or a custom topology, as well as then benchmarking this model on the STM32 using STM32 Cube.AI and STM32 targets, and then deploy this using the getting started or application projects that we provide for each of the use cases on a real board. I would be showing you very quickly the 2 tutorials today, which are available in the tutorial section in the notebooks. You can simply download these 2 notebooks and upload them in the Google Colab. To make them run faster and not spend so much time in the training, I have already pre-run the Jupyter notebooks and I have a screen capture. So I would be explaining step by step each of the sections and telling you how they work and what each of the section is doing. So for the first Jupyter notebook that I would show you, I will explain how you can use the models, the developer cloud through Python wrappers using REST-based APIs. So this is more for the people who want to use this in their Python applications instead of actually using the website or the web-based tool itself. To do this, you simply download this Jupyter notebook and you upload in the Colab, or you can run it in the local Jupyter server. This will be using the REST-based API services, just like the developer cloud GUI application. Here you can provide a model either from the Model Zoo itself, or you can upload a model from your local PC. Then you can optimize and benchmark your neural network model using the developer cloud through Python services. And finally, you will be able to generate your code which is optimized for STM32 targets. If you are running in the corporate setup and behind the proxy, you have to uncomment this code and run this by providing your proxy settings. But if you are running from your home or from personal PC, you do not need to do this. In the next cell, which I just executed, I have installed all the required packages or Python dependencies. Then I would download the drivers for STM32 Developer Cloud by running this cell. And these drivers are available in the Model Zoo. So you can either download from the Model Zoo or you can run this cell to get these drivers. I will make sure that this driver has been downloaded and are available in my Google Colab content tree. Next, I would run some helper and utility functions. These will include a list of different STM32 series for which I can generate the code, as well as this would include the 3 famous IDE or compilers, which are based on GCC, IAR, and Kale. As I told you that here we are doing again what we saw in the GUI with the tool, but now with the Python. So the first step is to provide your credentials to connect to the STM32 Developer Cloud. You can provide your email address just by typing it in, and then it would prompt you to enter your password. If you have an account already, okay. Otherwise, you can visit this link and you can create your account. Once you provide your password, we confirm that your password is correct by running the next cell where you try to connect through the web services to the cloud, and just to avoid the problems in the next steps. And now we will be doing the steps where we are importing a model from the Model Zoo in the workspace of your developer's cloud. The first cell would get the list of all the available models in the Model Zoo and provide you a drop-down option where you can select any of the models. For me, I would be selecting here the flower model again, because this is something which I would be demonstrating after in the live demo as well. The next section present a README file, which provides all the details about the model, the footprints and all the information. And the next cell would download this and put it in a .models or relative directory in your content tree. The next section would show all the contents in your .models folder. So here you can download the models from the Model Zoo itself, or you can upload your own model from your local PC to the Colab. For me, I am only using the model from the developer from the Model Zoo. That's why you see only one model. The next cell is going to upload this, and now it is on the stage where we have this in our workspace. Just like Model Zoo, we have 3 optimization options, which are balanced, time, or RAM, and we will be able to select any of them from the drop-down. The next section would run the analysis to provide you an estimate of your total flash and total RAM, as well as your computation budget in the form of max, which stands for multiplication and accumulation counts. So it provides total flash in the form of flash required by your weights, as well as the flash required by your code, as well as total RAM required by your activations, as well as the runtime. Next, we'll do the benchmarking on the STM32 targets. Here, we are getting the list of the target boards available in the form cloud form. And we are getting this information to make sure that we are getting the latest list. We are in the process of continuously evolving and putting more and more boards available in the cloud form. So here at the moment, we have 10, and we are getting this. Just like the developer cloud as well, here we are handling the use case where your model does not fit, for example, on G747. So it's showing you an error message, and it's for the rest, it keeps on going, and it's not stopping the execution. Once the execution is done on each of the boards, we plot a graph just like the developer's cloud to show you which of the boards is providing the best performance. Just like the cloud itself, here you see the 735G is providing the best performance, while the model does not even fit on G474. And for L4, it's providing the lowest frame per second. Then the other option is you do the benchmark on a selected board. Here I'm doing it on 747 Discovery. After it is finished, it also shows you the inference time and all the footprints. And finally, you can generate the code. For the code generation, this is downloading the zip file. And here we are showing you the first 20 lines of your code generation report. This is equivalent to do the STM32 AI model generate on your local installation of STM32 Cube.AI. Then you can delete your model from the workspace. And finally, you can zip these generated files, and you can download them by running the next cell. These are the contents of the code generation. You have all the files and runtime for your model, as well as all the information related to your model in the form of network.h and your network parameters in C. These are optimized code generated for your selected board and for your selected series. Next, which is the third part, and this is the most fun part of my session. Here, I would describe how you can take the model zoo developed by STM32, and you can actually use this model zoo to train a model for your image classification use case with writing almost no code at all. And then you generate the optimized C code using the developer cloud, and then embed this model on an actual STM32 project and flash the board to see the inference very quickly without writing a single line of code. So for doing this, I'm using the second notebook. Here, we will be demonstrating how to train a MobileNet V2 architecture with alpha value 0.35 and the inference and running the inference and training on the image size of 128 by 128. And we will be doing flower recognition using the TensorFlow flower dataset. First step is to do the cloning of the STM32 AI model zoo repository. Alternatively, what you can do to have to save space in your Google Colab or your Google Drive, you can do the cloning of the STM32 AI model zoo locally and provide only the contents which are needed, which are image classification / scripts folder, as well as the common folder and the requirements.txt. You can download them, you can zip them in the form of STM32 minus modelzoo.zip, and then you can upload this in your content space. You can uncomment these 3 lines and do the unzipping. After running one of the 2 steps, you should have a folder called STM32 AI model zoo. Here are the contents of this one. For me, I use the cloning of the whole repository. Next, I would do the installation of all the required Python dependencies and packages. To do this, I simply run the pip install command with -r argument and pass the requirements.txt file. This would install all the required packages which are needed. And after this is finished, please make sure that you press the restart runtime. Otherwise, you will have the previous runtime and not the latest libraries. So after doing the restart runtime option, you will load the latest files which dependencies which you just installed. Then you navigate to the STM32 AI model zoo / image classification / script / training. This is because we are going to do the training. As you see here, there are folders for the training, deployment, as well as for evaluate. In this particular notebook, I am going to show you how to do the training. And next, I would very quickly show you how you can do the deployment of the model that will be generated here. Again, here we are going to use the STM32 AI Developer Cloud Service. So we are going to enter the username and password to make the connection with the Developer Cloud to do the benchmarking of the board. The next step of doing the training is to get the dataset. Here we are going to use the TensorFlow flower dataset, but you can use any dataset Just make sure that your data set is shaped in the right way, which means that you have the dataset parent directory, then you have the subdirectory with each of the class names, and all the images corresponding to one class should be under the class subdirectory. The split between the train and test dataset happens automatically, but you can also provide the train and test dataset all already pre-splitted in your case. For us, we are going to use the flower dataset. You select in the drop-down the option for flowers, and then you run the next cell. This would automatically download the dataset, unzip it, and put it in the right format, which can be used for the script next to do the training. Just to show you that it has put the dataset in the dataset directory under training. And as you see, as I explained, I have 5 classes. So we have daisy, dandelion, roses, sunflowers, and tulips. To make the life of the developers easy, we provide all the configurations for the training at a single place in the form of a .eml file. Here you have different sections. At the start, we have general configurations, which include the project name as well as the place where your models would be saved. Then you have the train parameters, which include the batch sizes and the training epochs, as well as the run rate, the learning rate. And then there is data set information, where you provide the information about your data classes, as well as the flower dataset path. Then there are sections where we provide the information regarding the pre-processing as well as the data augmentation. The data augmentation is a very handy tool when you have small data sets and you want to artificially augment it to have bigger data set. Then there is information about the model. As I explained before, we provide quite a few public model topologies, such as MobileNet V1, V2, SqueezeNet, ResNet, ShuffleNet, and FD MobileNet. But you can use your own custom model as well. In that case, you just change the name for model to custom, and you provide different parameters for your configuration. You provide the input shape. We provide the option to do the transfer learning to train the model very quickly. Instead of training the whole model itself, you just train the last layer by keeping the feature extractor, which is trained on very famous data sets such as ImageNet. And we also provide the option where you mention if you want to do the post-training quantization. This is going to be done based on TensorFlow Lite converter. You just set the quantize flag to true and evaluate flag to true to do the evaluation on the quantized model. And you select the quantization input and output types. Finally, you provide the details about STM32 AI ecosystem. Here for the optimization, you can provide any of the 3 options: balance, RAM, and time, as well as you provide the footprints on the target option. This is one of the boards provided in the developers cloud from the 10 boards which I showed you before. If you provide this information, you do not need to provide path to your STM32 AI, which is the path to your local STM32 AI installation for the CLI application. But if you want to do all the checks and analysis locally, you can set the footprints on the target to false and provide just the path. Once you have made sure all the information here is right, you can simply do the training. For doing this, you simply run the next cell, which is going to start doing the training. Another thing I want to mention over here is that all the things in STM32 AI Model Zoo are powered by are using MLflow, which means that all your runs are logged in MLflow, and you can compare the performances of different runs without manually checking them by just using MLflow UI. Once you start doing the training, the first thing which happens is that we print the details of your model architecture, where you can see all the summary of your model, including the layers and number of total parameters, as well as training and non-training parameters. Here you see the trainable parameters are very few because we selected the option to do the transfer learning, and all the other weights are fixed or frozen. We do the fake quantization at the start because the quantization is going to provide the better result, and we selected the quantization option to be true. And then we do an analysis very quickly to guide you what would be your estimated footprints in terms of flash and RAM. This is very useful step, and we are doing it before doing the training because to avoid doing all the training and then finding out that maybe your footprints for this model are too big and they will not be able to fit on your board of choice. So here it has provided you, for example, the analysis information, which is using the balanced optimization, and it tells how much information, how much RAM and flash you are going to be needing, you are going to need for this model. Then we do the training. One can be a little bit worried to see that I'm doing training for 1000 epochs, but this is to tell you that we have already implemented a callback called early stopping. So this stops the training as soon as your training has converged, and you do not need to do all the 1000 epochs. In our case, for example, it would be running only around 53 epochs before it converges. So after it has converged and all the, it will plot the history of your training, which show you how the accuracy and the loss function has evolved over different epochs. You can see this, the loss function and the accuracy function look quite nice, which means there isn't any over or underfitting. Then it plots a confusion matrix, which provides you class by class accuracies. And then it does the quantization because we're selected to do the quantization on the real data. Once the quantization is done, then it starts to do the benchmarking on the board of your choice. And here you can see the information about the inference time as well as the total RAM and flash on a real STM32 board. Finally, it does the evaluation on the quantized model and display another confusion matrix for the quantized model, where you can again compare the accuracy between the quantized as well as the float 32 model. You can see the accuracy for the quantized model is 86.51 compared to the accuracy for the float model, which was 86.78. So this means the quantization has resulted in less than 1% of drop, which is quite impressive. Each of the runs, as I described before, is created in a way that you can compare this with the new runs. And at every run, we generate an output folder, which is named with the runtime. So here, for example, this was launched on this time. In each of the folders, we saved information about the confusion matrices as well as the accuracy and the loss chart for the training history. We also generate a header file which would be needed at the time of doing the deployment. This includes the information about the number of classes, the shape of your input, as well as the labels of the classes and the pre-processing settings, such as if you are going to do the resizing of the image, or if you are going to do the scaling of the image and with what offset and scale. Finally, you can zip this output file and you can download this either manually, as I am downloading over here, or by running the next cell of your Jupyter notebook. Once this is downloaded, this would include all the information over here, and we can use this information or this trained model and deploy this on an actual STM32 AI on an actual STM32 MCU board. For this use case, I would be using an H747 discovery board. So I have downloaded this and I have unzipped the files. And as you see, it contains all the information which I have shown you before. I have done a local clone of STM32 AI model zoo, and here are the contents. You can open this in the IDE of your choice. I am using here the VS Code. I would open the image classification folder and would go to the scripts and deployment section. Here we provide a README file which describes step by step all the things which you need to deploy this on an actual STM32 board. We also provide an application package called Getting Started, which includes all the embedded code and STM32 Cube.IDE project, which would be needed to run this on an actual board without you writing a single line of the code. Here, for example, we provide all the settings and configurations exactly in the form of user configuration.yaml, but this time for the deployment. Just like training, we also, for the deployment, combine everything and all the configurations in one single place in user configuration.yaml file, and you provide all the configurations which are similar to your training configurations to have the best accuracy or to have the same accuracy as you saw in the training time. Here we are going to use an H747 discovery board, and we are going to run only the Cortex-M7 because this one is a dual core board with M4 and M4, but we are going to use only M7, and you are going to use the camera module, which is called BCAM's OMV module. So simply connect your camera with the board and plug your board with the PC itself, and you are ready to flash it. Just make sure your configurations are right. For example, here, make sure your class labels are correct, because this would be used at the inference time. For me, I don't need to change anything because the default configurations that we provide are actually for the Flower dataset. So I would simply provide here the path to the quantized model that I just downloaded from the internet by running the Jupyter notebook. I would change the backslashes to forward slashes because I just like forward slashes, but it would work even without this. You provide your TF-Lite model path. And the next thing you need to configure is to provide the path to your STM32 Cube.IDE. This one is needed to build the project as well as to flash your board. I would simply provide the path to my Cube.IDE. You do not need to provide the path to your local installation of STM32 Cube.AI CLI application. If you are setting the path to your footprints on the target, because then this would be using the developer's cloud directly. If you want to use only the local installation, you can set the footprints to false, and you can choose this option to be true. Similarly, here you can provide the optimization setting for balance, time, or RAM, and you can provide the target series, which is H7 for our case. And the path to getting started is already pre-provided here, so you do not need to change anything. You simply go to the folder for the deployment, and you execute the command python deploy.py. As soon as you run the command, it would connect to the cloud, and it would do the benchmarking again to give you feedback on your inference time, as well as your required or consumed RAM and flash. Then it would start generating the C code. Once the C code is generated, we have written the wrappers or the drivers for the Cube.IDE, which automatically takes your generated code and copy it to the right location in the getting started folder. For example, here we are copying the runtime, and here we are copying the network parameters and all the information, as well as we are copying the AI model config.h file, which would be used to make sure that we are using the same pre-processing settings as they were used at the time of the training of the model. Remember, this was the file which I generated from the developer cloud. Now I can show you very quickly that I have already deployed it on STM32 AI target board, and I can show you how it works. So here you can see the application running on actual STM32 discovery board, and we are doing the flower recognition in the real time. You can see the FPS is around 9 as told by the benchmarking, and inference time is around 111 milliseconds. And here we are showing the class label as well as the accuracy. So this is as easy as this to develop and to deploy the STM32 projects with your AI applications and have and provide the AI to your edge. Now I will hand over the talk back to my colleague Nicola, who would provide you the resources which you can use to connect to STM32 AI.
Yes, thanks a lot, Shanawaz, for the very cool demonstration. I hope people in the audience now can't wait to deploy their own embedded AI use case on an STM32 Arm Cortex-M based MCU. Just to mention that we are sending in the chat a link for a short 6-question survey from STMicroelectronics. Please take this opportunity to get in further contact with us and to let us know your feedback about today's webinar. Thanks again. I think we have been longer than expected, so hopefully we can have 1 or 2 minutes for the Q&A session. Thanks a lot.
No worries. Thank you, Nicola, and thank you, Shanawaz, for a fantastic tech talk and really engaging, great demo. I'm sure that people will have been following along, and then, because we've got the recording, will be live on YouTube immediately afterwards. You can always scrub back and copy bits in and sign up and register and get everything sorted. So thank you for that, and thank you also to the folks from ST who've been answering questions as they've come in the chat. So really appreciate all the answers that have come in. I think looking at the questions, just looking at those you've answered, they kind of cover a good few things. I guess one of the things I wanted to touch on briefly, and I think you've touched on this as well in the chat, as well as around the sort of security and privacy of the AI models that developers use, right? So could you just touch on how you, with the tools you provided, ensure that those models developed by developers when they add them to the cloud are secure and private? I know you've alluded to it in the questions, but Nicola, good to go through that briefly.
Sure. Yes, thanks a lot for this question. I think that's very important indeed to address this topic. We know that for some of our users, this is definitely a concern. So just want to remind here that all the models which are uploaded in our developer cloud, they are managed in a private Azure storage service. They are accessible only by the user that has uploaded the model. In no way we at ST can access the model. These models, when they are not used for a 6-month period, they will be deleted from our cloud, not accessible anymore. And all the data which are used only for the time of the computation, for the time of the usage, as soon as we are done with using them, as soon as the cloud is done with using them, they will be also removed from the cloud. More details are available in the online platform, in the documentation section for model and data storage.
Thank you for that. And of course, you support a lot of the boards you support on the developer cloud. It's a great range of them, all the Cortex-M zeros, M4s, M7, a lot of them. What if there's a board that a person looks at and says, oh, actually, you know what? I can't find that STM32 board I'm interested in that developer cloud. Is there a way you can help?
Yes, indeed. So it's true that today we are already covering, let's say, a quite broad range of processors and MCUs. In the event that the board you are looking for is not part of the board farm, well, the easiest way to do it is to reach out using our email address that is actually here on the screen, and telling us, okay, what is your use case, what you would like to do. Maybe we can advise, and if needed, we can discuss how we can help in adding the board in the board farm. We are, as I said, we are continuously adding new boards, so maybe this is already planned. So yeah, let us discuss.
Thank you for that. That's brilliant. And I think, as you say, I think we're now we've gone into a couple of minutes of extra time, but well worth it for the questions. And thank you to you and the team for answering all the dozen plus questions we've had in the chat. So thank you again, Nicola and Shanawaz from ST, for a fantastic ARM Tech Talk. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem, with a really great presentation today and fantastic demo. So I hope you've enjoyed it as much as I have. And thank you to the whole team from ST for a fantastic tech talk today. And audience, we'll look forward to seeing you in a couple of weeks' time at our next ARM Tech Talk. If you want to sign up for that, just head to arm.com/tech talks. All the upcoming talks will be available there. So, Nicolas, Shanoaz, thank you so much again for today's tech talk, and we'll see you all again very soon.
Thanks a lot, anyone. Bye-bye.